Okay, everyone, so today what we're going to do is, first, I just want to show you the updated calendar here. And you have, if you want to do this R bonus assignments, I have them all posted and open now, except for the very last one. So you can just work ahead and try these if you want to do them. But don't feel obligated to do these. They're only for bonus. And they're worth about the same as a survey, and a survey takes you 2 minutes, and this will take you probably, each one of these will take you at least a half hour, I would say. So just, if you have other things you want to do and you're not interested in learning R or seeing it, what it can do, don't feel obligated to do these. As always, these are just for bonus points. It won't hurt you if you don't do them. All right, but if they're fun if you want to do them. Okay, now, I also want to show you that the exam key is posted here. So if we go to the exam schedule, and here is your keys posted right here, and the class did very well this time, better than on exam 1, which you also did pretty well on. So things are, seem to be doing, I mean, for the amount of material that's being covered, I'm impressed at how well people are doing. Okay. So now let's go to the document camera. And so what we're going to do today is we are going to look at what to do when remember the assumptions that are required to do these T, Z, F, and chi-square tests. First of all, I want to make sure that this, can you hear me? I want to make sure this is recording. Can you hear well? Does it sound like it's on? Okay. So, to do these tests that we've been doing, the T, Z, F, and chi-square, they all depended on these assumptions, that the data was collected by a random process, our scatter plot was linear, and that the errors in the regression model are independent with equal variability and follow the normal curve. So, we talked about these in chapters 26 and 27 and 36. So now we're going to look at what happens if some of these assumptions are violated. So this randomization test has the advantage of not requiring all of the assumptions. It still requires this test requires linearity. Randomization test it still requires linearity. You should still make sure that the scatter plot looks linear, but it doesn't require the assumptions about the errors being normally distributed and with the equal variance, etc., because it doesn't, it's a distribution-free way of doing to test the strict null. So what we do with the randomization test is get p-values by creating computer-simulated distributions. And you'll see what I mean in a minute. So, so instead of computing the test statistic by assuming these theoretical underlying normal distributions like we do with the T and the F, or a big enough sample size that the central limit theorem kicks in so we can assume normality, it doesn't do that. It doesn't rely on theoretical distributions. It just relies on empirical, experimental distributions that we're going to create ourselves. So it has another advantage pedagogically in terms of being able to really understand what's going on. You can just see these distributions being created, and you can then get p-values to test the null hypothesis that the correlation is 0. So let's look at how we do this. So we're going to go back to the example that we've been using before, the same example where we saw that the homework and finals in a group of 107 students were correlated. And we had this correlation right here. That's what we found. And we also found this sample regression. That's what we've been doing. We've been working with this example a lot. So now, remember what our null is here, that in this case, that the final scores are not related to the homework scores, that the correlation, that the correlation in a population is equal to 0 in some wider population. And the alternative was that no, that they are related, that there's a non-zero correlation, okay? Now, we're not going to be talking about a wider population. What we're going to do is look at within our 107 students, the null says that if there's really no relation between your homework and final scores, then you could expect any one of them to be, any one of the 107 final scores to be randomly associated with any one of the homework scores. So what if we just break the connection between the homework and final scores? We have these XY pairs, right? We have what you got on the homework, that's your X, and then what you actually got on the final. And they're paired up. These are the first 20 out of the 107 people, right? So this is the first 20 students. I just didn't want to write down all of them, but I want to show you what's going on. So right now, this student didn't do very well. He had a 30 on the homework and a 52 on the finals, etc. These are the actual pairs right here. Right here is the actual XY pairs. But what we're going to do is, remember what the null says. The null says that there's no correlation between homework and finals. So if that was so, then we could just randomly assign the actual finals and the actual homeworks, just scramble them up and just assign, for example, just pretend I just randomly take these finals, and I'll just closing my eyes and I'm just picking one. Okay, 72. So I'll assign that to this one. I'll do it again. Okay, I get 46, etc. All right? And I pretend I do that for every single one of them. Okay? Now I have these these random Ys. These are random Ys. Okay? So here we have the actual X's, and we have the random Ys. So this is the X and random Ys. And the null says that the actual pairs that the students really got, this pairing, what they actually got, is no more likely than just X and random Ys. That's what we're testing. We're seeing that, okay? So imagine putting all the final scores inside a box and randomly choosing and assigning it to student 1. That's what we do. Then what are we going to do? Then we're going to compute a correlation between, we'll compute a positive correlation, the R. We're just looking at the R here, between the 107 homework and scrambled final scores. So what we're really doing is we're testing whether our observed sample R, which is this is a two-sided test, right? So what we're doing is, this is a two-sided test. So I'm saying, remember what R is? R is only positive correlation. So if it was a negative, it would just be, it's just looking at the absolute value. So this is equal to the absolute value of R. So it's the same as for a two-sided test. And the reason I'm using this R is because we're also going to remember that it's also the correlation between our actual scores and the predicted. So the actual final scores here that the students got and what we predict according to our model. It's the same thing as the correlation coefficient. It's just the positive one. And the reason I'm using this is because we're going to extend it to multiple regression, where it's the only type of correlation that makes sense. Okay? So I'm using it here for simple regression. So we're testing whether our observed sample R that we actually got, the students actually got, is much different than the R's, than the correlations we'd get by randomly pairing them, by scrambling them, by randomly pairing the X's and Y's. Remember, the null says that it's no different, that it's just due to random chance. So we're going to enact this, okay? So what we do is, let's say we did that 1,000 times. 1,000 times. We'd have 1,000 R's, each computed from 107 homework and scrambled final pairs. We could then make a histogram of the 1,000 R's. So this is like an actual histogram of what we got. It's an experimental or empirical histogram. So it's an empirical sampling distribution of R. It's a histogram showing all the R's under the null. It says it's just due to random chance. Do you understand the idea? So let's turn the page, and I'll show you what the histograms look like. Okay, let's look at them. So when we turn the page, so what do we have here? We have a histogram of 1,000 such R's. And then we have our sample R, which is right here. This is the sample R. The R we actually got in our sample, not through randomization. This is what we actually got right here. We got pretty high R, not through, that's this right here. That's what it is. Okay? And why is the p-value 0? Because we didn't, through all our 1,000 randomizations, we didn't get one that extreme, that high. We did this 1,000 times and we got a lot near 0, where you'd expect, why would there be any correlation? You're just randomly scrambling, pairing the X's and Y's, right? So why would there be any correlation? But this is our p-value here. It's 0 after 1,000. Does people understand that? Questions? Okay, so this was just a histogram. We got one way out here that was close. Looks like there's one way out that was close, but we didn't get any that was that extreme. So so these are after 1,000 randomizations. So this is the actual histogram. You know, it's going to change each time. See how it's really jagged? It's not a theoretical smooth histogram because it's going to change. You know, the more you do it, the smoother it will get. Like here's after 100,000 R's were computed. After 100,000, note the p-value went up a tiny bit. We did get one here. That's because after 100,000 times, we did happen to get a few R's just by the luck of the draw. Okay, so that's the same thing here. All right? And it's the exact same thing. So we got a tiny little p-value here. It's going to change each time. Does that make sense to people? So, do you want to see it enacted on the computer, or you do understand it well enough as is? Raise your hand if you want to see it enacted on the computer. Want to? Okay, let's try it. So let's go to our data program and look at this. Oops. Let's go to our data program here and look at this exact example. So we'll go to regression. And, oops, first we have to choose this example. So this is the grades. Right here, and now we'll look at regression. And we're going to choose as our y variable the final, and as our x the homework, right? And here, what do we have? A chi-square and z, or we could have an f and a t, and it's giving us very low p-values. And here's where we got our r that we're using right here. That's what we actually got in our particular sample, right? There was a correlation between the homework and the final. But now let's look at the re-randomizations. So after 1,000 re-randomizations, now this is using r, not the absolute value of r here. So it's probably easier for you to understand. So it's using r, and here some are negative, some are positive. They're evenly distributed around 0. And here we have our sample r. And what was it? So far, none. But let's, okay, so that's after 1,000. Now what happened? After 3,000, we happened to get 1. You see? We just happened to get 1 right there. So now we have a tiny little p-value. So if we do it again, let's do it after, what do we have, 100,000? Let's see what we get. That's what's displayed in your, look, we've got 1. We got, it's 71,000. We've got something. See how it's starting to look more and more smooth. And let's keep going. Yeah, it does. I mean, this changes each time because it's an empirical distribution. But you can see how unlikely it is. Also, you should be totally amazed that a computer, that, you know, it happens so quickly. Can you know what it's doing? It's taking 107 and each time computing a correlation coefficient between them, and it did 100,000 times just like that. It's pretty amazing. So what the advantage of this is, if you don't understand, you know, you can just check it out. You can just look at these simulations. You don't have to assume anything about the underlying distributions that these variables that x and y come from. So it's, and also you can, it's fun. I mean, you can just do computer simulations to understand stuff. And to, I love it. I mean, it was what I dreamed about years ago when I studied statistics, that someday we'd be able to do this and really just, you know, because your assumptions are often violated. And you have to, you know, you don't know for sure. It's very, very, you don't have usually textbook perfect cases of assumptions being, you know, not violated. There's always some gray area. And so you can do this and check what you get by the chi-square or the F test, and or the T or the Z, and compare it to this. I mean, that's what you should do. And just about always, they should agree. They should agree. And if they don't, then you've got something strange going on. So it's a great way to check it out. It's very useful. Okay, so that's the idea. Any questions now? I hope that helped, seeing the computer simulation of it. And so now we're going to go back to the camera. Okay, so now we'll do the same exact thing with multiple regression. It's totally the same. All right, so what are we going to do here? So here we found a very high correlation. It's going to be, and we got a very low p-value when predicting finals from both homework and exams, as you would think you would get, right? So here's our sample regression that we got before, and here's our null and alternative again. And so now we're going to do the same thing. So what do we have here? So now we have the same 20 students here, and here's their homework and exams, right? And then what we're going to do, and here's their actual finals. So this is, so you think, okay, so this right here, for the first 20 students, is their paired x1s and x2s. So these are their actual or paired X1 and X2, homework and exams. Okay, we're going to keep those pairs together. Now what we're going to do is we're going to take their finals right here. So right here, let me just show you what we've got here. So we computed our R based on, of course, their actual paired X1 and X2, and the Y's. So we have X1, X2, and actual Y's. And that was our observed sample, R, that we got. We got an extremely high R here. We got R equals 0.6198. Now what we're going to do is we're going to get a p-value for this. And we have to use the capital R here because we have 3 variables. I mean, we have 3 sets of numbers, and we can't compute a correlation coefficient. So this R is the R between their actual Y's that they got and what we predict when we do a least squares regression. Okay? So now what are we going to do? Now we're going to scramble these again. So we're just going to randomly, I'm just going to close my eyes, and here's 60 for the first person. I'm going to do this with everyone. You know, you just do it 76 for the next, and, you know, each time you're going to get different things. So now we've got the scrambled Y's here. And what we're going to do is we're going to take this. Now what do we have? We have the X1 and X2, these actual paired. And then we have the random, at least the random Y's. And what we're going to do is we're going to get a least squares equation. We're going to get different betas each time. We're going to make a prediction based on their actual paired X1s, X2s, homeworks, and exams, and we're going to be predicting these scrambled Y's, right? So we'll get different betas predicting, we'll get some prediction, and then we have what their scrambled one was, and we're going to see how close they are. We have 2 sets of numbers, these scrambled Y's, and then we're going to see how close they are to what we would predict just by, you know, doing a least squares fit for each randomization. So we're going to get, and then we'll get of course, we'll get this correlation, we'll get these correlation coefficients that are based on the randomizations. And then we're going to create histograms, the same exact thing we did before. Okay, no different. So, so let's say we did this 1,000 times. We'd have 1,000 R's, each computed from their actual paired homework and exam scores, predicting their scrambled finals. And we can then make a histogram of the 1,000 R's. And now it's going to be really unlikely. Look how far away the randomizations come. Now they're all positive because these are capital R. Okay, so again, what is this? So right here, right there, is our observed sample. Equal to that. It's the same as that. So it's the R we really got. Not through scrambling anything. So but remember what the null is. The null says it might as well just be through scrambled stuff. It's just due to random chance. So what I love about this re-randomization test is that it actually enacts the null. It's saying this is the sampling distribution you get from the null. Let's empirically do it so you can completely understand it and see how wildly unusual it is. So then you say, hey, we reject the null because look how far out we didn't, look how extraordinarily far out it is. Doesn't that make sense? So it's so far out that, so it's so obvious to reject the null. P is approximately 0, so we feel with tremendous confidence to reject the null. Overwhelming evidence that we understand. We know what these randomizations are doing because they're not based on anything except the random pairings that we can see happen. Okay, does that make, you don't have to you don't have to understand the underlying statistics. Oh, a child could understand this. If you spent some time and showed them, enacted it. You could teach this, I would love to teach this in like 5th grade, 6th grade, actually hands-on, scrambling them, taking, 2 sets of numbers, shaking them up and pairing them and doing it over, making little histograms. They could understand this. And I think it would be really important because randomization is the key idea behind all this. Sampling distributions. They could make little, I would love to have, I wish that's what should be taught in the schools, and then it would be, you just have this bedrock, gut level understanding of what statistics is about, really. I mean, the key idea of variation, random variation in sampling distributions. So this comes very close to it, so I'm really glad to be able to have the computer power these days to show people this. Okay, so that's the idea, and here we did it after, whoops, this is after a typo here. This is after 100,000 randomizations right here. And it's a smoother curve, right? Just because we have so many. And still, it shows. Okay, so this right here again, that's our observed R, our observed sample R equal to 0.6198 right there. All right, so I think you get the idea, and you can play around with it yourself with a data program. And if you don't trust, like you're not sure about these distributions, you're not sure whether the central limit theorem is kicked in or whether you have what the distribution of the underlying of the whole population is, this is good to see if this is in agreement with what you get by the F and chi-square test. Okay, so in general, the randomization test is the most conservative because it makes the least assumptions. So in general, it requires the strongest evidence to reject the null, but that's not always the case. Now what's this? Okay, so what's the downside of doing this? Why don't we always do it? The downside is that you don't get any parameter estimates for the individual slopes. All you get is a significance test for the overall regression effect. That's all this gives you. And many, many times you need, so it's good as a check for the overall regression test, but it doesn't give you the individual slopes, to build a model. Okay, so that's the downside. Any questions on that? All right, so now we can do the same thing with ANOVA. Exactly the same thing with ANOVA. So this example comes from, this is the same example we did in chapter 21. So this is our chapter 21 example 2 on page 109 to 110, where what we were doing was we were testing whether these group means between whites, blacks, Hispanics, Asians, and mixed and others on their ratings for what their feelings about gay marriage were with 10 meaning strongly opposed and 0 meaning completely for. We wanted to see whether these differences were significant. The null is that they're all the same in some wider population. But if you recall, we didn't really sample from a wider population. And that happens a lot. We're just saying, okay, we're assuming we did. So now what we're going to do is actually create a randomization. And so we're going to look at an empirical distribution where what we do is we take the actual, to test this null, that the attitudes towards gay marriage are unrelated to ethnicity versus this two-sided test here. What we're going to do is we're going to take the 858 students, their actual ratings, and randomly assign them to the 5 groups. There's 5 groups here. So for example, let's say we have the 850. We shake them up, we shake up those ratings that people actually gave, and then we'll assign the first, we'll draw 448 out randomly and assign them to the white group and take their average of the scrambled ones, right? Maybe it's better if you read along here. So I don't want to go too fast. It's easier to see it written too. If there really was no relation between the attitudes toward gay marriage and ethnicity, then we could expect to see any one of those 858 ratings randomly associated with any of the 5 ethnic groups. In other words, we could scramble up those ratings, the 858, and then randomly assign them without replacement to these groups. So the first 448 ratings that we pull out, you could do it in any order, but let's just say we did it that way. Just randomly divide them according to these numbers, take their average, and that's what we'd have here, the average rating for whites. Then we'd take 84 out, and that would be, take that average, and we'd have an average for the blacks, etc. So we just would randomly divide them into 5 groups with these proportions, right? With these numbers, and then each time we're going to get different averages. They're not all going to be identical, right? And then we get a sampling distribution of all those R's each time. So what is, so let's see, okay, so now the p-value is the chance we'd see an R is extreme as this, which we got before, back when we looked at it, as extreme as that just by random sampling. So here it is again. This is the R we actually got. And it's the correlation between people's actual and predicted. So remember, the predicted are just based on their group. So that's what it would be, and look at it. It's so far out there. So far out here. The p-value, again, the p-value is almost 0. So we reject the null. It's just so, none of our randomizations are this big. So what does that tell us? It tells us that it's not, that there is an association between the ethnicity and the ratings. It doesn't tell us if it's causal or not, but it does tell us that there's an association very clearly, because we did it. Look how many times we did it. Where's 100,000? We did it so many, and here's a histogram of 1,000 and 100,000. I only have one. This must be the 1,000. Where's the 100,000? I'm sorry, it must not have come out. Here's histograms of the 1,000. This looks like the 1,000. Sorry, that's a typo in here that I didn't have the other graph. Sorry about that. Any questions on that? So here's a way that I like to think about this is, like, whenever, throughout I've been saying, even though we've looked at data from our class, it was, from the Stat 100 class or Stat 200 class, our own survey data, a lot of data, it wasn't randomly chosen from a wider population. most of the stuff that we've looked at, except for polling examples, weren't really randomly chosen from a wider population. So we don't really have a random sample. So what are we doing here? So you can think, in this example, we didn't have a random sample, and we didn't have a random assignment to groups either. You know, you weren't randomly assigned to different ethnicities, right? So technically, we're really not supposed to do a significance test. But people do them. The only time that we really, you know, could do it technically would be when we have a randomized experiment or actual random sampling. But here's the thought process where people do it anyways. And I think that this example, the re-randomization, helps you understand it better. So you picture one of these two scenarios. You either picture this, what we've been doing, an imaginary large population of all possible Stat 100 students from which the 858 students were randomly drawn, right? And that's what ANOVA and regression, that's when the F and the chi-square statistics, all the ZT, all assume this, right? And the null is there's no real difference between the mean group attitudes and the imaginary population, okay? So then we look at that's what this is doing. But now what the re-randomization test does is sort of create an imaginary randomized experiment. So it says that knowing which ethnic group someone's in tells you nothing about their attitude towards this issue, nothing. So, and if this were true, you could just randomly take the attitudes and all the people and randomly assign them to the 5 groups. And it wouldn't be surprising to get the differences that we got in group means. So we simulate that, and we see that it is really surprising. We don't get that. So this is what the re-randomization does. So there's 2 ways that you can, what I like is it makes it, this is what the randomization test does. It makes it so you really have to explicitly think about what you're doing, how you're doing these randomizations, and then you can visualize it. That p-value has more meaning. Okay, so ANOVA assumes the first one and requires certain assumptions, right? And this one just enacts the second. The randomization test enacts it. And so it doesn't have to have those assumptions about the wider population to be valid. It's really cool that way. Okay, so that's the idea. And what I like to use it for is to check. They should be very close. If they're not, something strange is going on, and you need to figure out why. What's going on? Okay? So, and in our examples, they were very close. Okay, questions? Now I said that test assumes linearity. Why? Just think about it. Let's just go back to the first one, to the very first example here. Where did I say it assumes linearity? Right here. It requires linearity because what are we testing? What if we had something like a real pattern? You know, here's X and here's Y, and we have this real pattern, like this. This correlation, this test would not be appropriate because you could still compute a correlation coefficient. What would it get? You'd get a correlation coefficient, R equals 0. Whereas what you're really interested in is the pattern between X and Y. And this has, you can almost perfectly predict Y from X. It's just using a curve. So this would be a terrible test to use because it would test whether R is 0, and it would give you that R was around 0. Even though technically R is 0, that's not what you want. You're trying to look for a pattern between X and Y. So this requires linearity. But what if you do have a curve? What if you have non-linearity? Then what do you do? Okay, so that's our next section. Transformation of variables. Transformation, so what we're trying to do is fit a linear model to nonlinear data. Are we stuck? Is there anything we can do? What can we do? Well, we could fit a curve. We could do that. We could fit a curve. You don't have to fit a linear model, or sometimes it's best to transform the data to look linear, to be linear by a transformation of variables. And then it will be linear in your transform variables, and you can use that to get the betas that we always do. Okay? But they'll be on the transform variables, so we can see how that works. That's what this part is about. So, to check, you need those assumptions. So the 4 assumptions, you need to use a linear model for inference. The first is linearity, and then independence, equal variability, and normality of the errors. These are all about the errors. But first, it's inappropriate to fit a linear model to nonlinear data, right? So we want to check whether the relationship is linear. So it should not show curvature, because then we can do better. We should fit a different model or make it linear by a transformation of the variables. So the ideal, we talked about this before. This is the same as chapters, but it's good to, this is the same as chapter 26 and 27. It's the same. But I just want to go through it again just to make sure you understand. So you have this ideal. Let's just look at positive quadrant here. So you have this ideal scatter plot that's nice and linear and looks something sort of elliptical shaped, like that. Okay? And that's x, and that's y, and that's your ideal. But often you get data that doesn't look like that. For example, you often get something like, especially in medical data, this J-shaped curve that kind of looks like, starts off with a negative correlation, and then it seems to go up and get a positive correlation here between things. Like, for example, your X could be some dose, how much drugs, how much like chemotherapy or something like that you're taking. And this could be the death rate. So if you don't take any of the medicine, you're going to have a higher death rate. So then the death rate goes down. But some of these drugs are so damaging to other, not just to the cancer, but to every part of your body, that if you take too much of it, it starts being worse than nothing. So if you have something like this, what would our linear model do? It would fit a line like this. And why is that bad? Well, because in the middle, we would overestimate the death rate here, and at either end, we'd underestimate it. So we could do much better. Another one that's really common is a curve that would be like, you see this all the time, that has an initial strong effect, like something like this, but then it sort of saturates and tapers off like this, so you don't get very much more the more X you apply. So what would this be? This would be like something like, there's lots of very compelling, interesting data on how much money you make. That could be X. That's dollars. And happiness. So happiness, we can put a little smile there for happiness. And what it does is, why is this? Well, if you have zero money, it's going to your happiness is going to sharply rise. You know, you have no money, that's pretty obvious. But what happens is, that's very interesting, is the more money, at some point, more money doesn't make people happier at all, even though everybody thinks it does. It just levels off or even can go down. But in the beginning, you know, between 0 and 40,000, there's huge effect, like or something like that, family income, especially between 0 and 20,000 and 30,000. If you have no money, it's terrible. So it's like, this would be bad too. So these are both bad. And so we're going to look at ways what we can do to transform data like that. Now, what about independence of the error? The errors in the true underlying regression must be mutually independent. Can we model our data as random draws from a larger population, or as random assignment to an experimental condition, kind of like what we just did with the randomization test? We did this latter one. So what do you want to check? You want to check that the residual plot shows no grouping. And so here's the ideal plot again. I'll just say you can always do that, but what would be bad? There's a lot of time-dependent data that's bad, that the errors change as x gets bigger. You know, they either go up or down. There's a lot of, easiest to understand would be like clumping, a lot of identical twins or something in your data set. So you would have like, it wouldn't look like this. It would be like there'd be clumps. You know, you'd have a few scatters here, but then you have like really strong clumping. So you don't really have as many data points. So this is bad, too. Because you don't really have as much data. If they're all, these aren't a lot, you know, if you had somehow grouping like that. All right, and then the equal variance. Again, that's a good plot up here. And a bad one would be something like a fan-shaped plot. So bad would be, you have a y and an x, and we'll examine stuff like this and what to do about it. And a very common way for this to happen is, remember, you want equal, let's say you have some regression line here, but you don't have equal variability. You might have very low variability. A lot of our data is like this. And then it fans out. And it can fan out in either direction. It could, you know, have the low variability look like that. So that's the fan-shaped. I don't mean to have clumping in there, okay? It's basically, that's the shape. And what do I say here? It's to check these assumptions, you can look at these scatter plots, but it's usually easier to spot assumptions violated in the residual plot. I'm not going to draw the residual plots here, but why would it be easier to spot it in the residual plots? The residual plots, remember, plot the errors. So it's almost like straightening that out like that, and that would be centered at 0. It's just because the y scale can change. So if there's very, very slight curvature, it might not show up until you expand this y scale out. Remember the errors here. I'll just draw one residual plot so you know what I mean. Okay, what would a residual plot look like? Well, the residual plot. I can do it for this one. So its residual plot would be like, you have here, you have the same, so here you could plot the errors, the residuals here, right? And they're centered at 0. So you're going to have positive and negative, right? And you could either plot them against x or y, really. But so you're going to have, like if there's very slight curvature, you can expand this, change the scale here. But if I didn't, it would just look like so it's just straightening that out. Okay? But these are the errors instead of the y's here. And you could have the x's here. All right, so any questions so far? Any questions so far? You're going to see one in your homework like this. In your first homework on these data transformations, you're going to get this data set on the solar system, and it's going to look really linear. But until you actually look at the residual plot, because then you'll change the scale, and it's like a magnifying glass on just the errors, because the errors it's very tiny little errors, and they show a very clear pattern. So you'll see what I mean after you do that homework. So this is going to be like homework. What are we up to now? 20 so far? So this would be in 21. It's not posted yet. it's going to be on the solar system. So you'll see that there. Solar system data. You'll have to look at the residual plot, that's why. All right, and this last one, normality of the errors. The errors around the regression line at each value of x are approximately normally distributed. So what do I mean here? Okay, so you have, let's say you have a y and an x. Now I'll draw this ideal plot again. What should it look like? Well, okay, so here's the outline of it. You know, it's kind of football shaped, right? And you're going to have this regression line here. And what I mean normally distributed is the errors. This is your prediction. Your actual minus your predicted are your errors. And these errors are going to be close to, most of them are going to be pretty close. They'll have, you know, residuals of 0, close to 0. And then as you go further out, there'll be fewer of them, right? And if you look at any vertical strip, you can think of it as normally distributed. Like there aren't many, if you do a histogram of it, there aren't many real far out. Like 2/3 of them are between 68% or between 1 standard deviation of the errors. 95% are within 2 standard deviations. You know, there's very few out there. It's going to resemble a normal curve. So you wouldn't draw a residual plot here. You'd take the errors and you would draw a histogram of the errors. You take a histogram instead of a residual plot of the errors. And you'd want them to look like what? To be centered at 0. Most of them close to 0, like the normal curve. Okay, that's what you want. Otherwise, it's a violation of normality of the errors, which is, people say that that even the f-test and the t-test are robust against that. That means there can be some violation of it as long as it's roughly normal. You don't want crazy outliers. But so what would it look like if it wasn't normal? You could have like something like, well, let's say you just had the same plot. But somehow, like you had like errors really far away or something, and nothing, very few in the middle, like that. In any vertical strip, it would look like that. And then it wouldn't look normal. It would be like your histogram of the errors would be what? You'd have big errors here, 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 here. It would look something like that. That would be bad. And this is good. Tab within the. This is the least important of the. But this is required to use the t distribution when you have a small sample. All right. Now, I think this is better understood if you look at real data. So, and what are we going to do? So here's, there's no hard and fast rule, but I just laid out some steps that are useful to me and are sort of standard. So transforming a nonlinear scatter plot into a linear plot by re-expressing the variables. So if the scatter plot follows a nonlinear pattern, so we're in this situation, we're not talking about the errors yet, we're talking about in this situation, it has a nonlinear pattern. It doesn't look linear. It doesn't even have to follow those pretty curves. It just does not look linear, right? Try the following 6 steps to make the plot more linear and to make the errors around the regression line normal. All right, so these steps 1 through 3 are going to try to make the plot linear. So it just doesn't look linear at all, okay? So you might want to start with transforming either the y's or the x's, right? There could be multiple x's. Why don't you just start with the y because there's just one of them? So that's what I would do. So transform the y variable. So you look at, because you're just trying to decide which variables to transform. to make the plot look more normal. So, I mean, to make the scatter plot more linear. So first start with a histogram of the y's. And if it's symmetrical, leave it, and roughly normal, just leave it. It's good. So if it's symmetrical, it's fine. Just leave it and move on to the other variables. But if it's right skewed, let's just look at the positive here. So if it's right skewed, what do I mean by that? Long right-hand tail. So something like, whoa, like whoa, 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 like this, like way long right-hand tail. Then what we want to do to make it look, you want to make it look more normal. So you want to bring these far out values, these ones in. So you could take the square root, like the square root, if 100 would bring it to 10, right? So that would work. That's a mild. If you want to take a more extreme, if they're really far out there, then you would take the log. Like if we were doing log base 10, well then like 10 to the 6th would, you just take the log, it would be 6. You know, 100, like let's say you had 0 here, 0, 1, and then you had 10, and then you had 100 out here, and then, well, pretend it goes really far out there, okay? How could you fit it all on one graph? We're going to take a look at this in a minute. Let's say when, you know, well, 1,000,000, so 10 to the 6 would go all the way to 6, right? 100 would go to 2, and you could fit this graph, and then it would look much more normal. The real extreme version, but it reverses the direction, is to take the reciprocal. But that's rarely done. It's not ideal because it switches the direction. The biggest numbers become the smallest. So it's confusing. So if it's left skewed, what are you going to do? If it's this way, if it's left skewed, why did I put that there? It's still positive. If it's left skewed, like our exam scores are kind of left skewed. There's people who do get really low down here, but most people are up at the top. If it looks like this, then there's sometimes they're so clumped together at the top, there's no discrimination here. So you want to spread them out. So you would take squared, cubed, or even, this is a real extreme version, to use as an exponent. So, but that's really unusual. So these are all the y variables. I'm plotting y along here to first transform the y variable. So if we squared it, then if you got, you know, these are all going to spread out. So you can get more discrimination at the top here. All right. So then you look at the scatter plot with the transformed y and see if it's linear. If not, you try doing the same thing with the x variables. If it doesn't work, we'll do this in a minute with an example. If the data is straight enough, you fit a regression, find the residuals and the predicted values, etc. And then, once you've done that, then you have to look at the errors. But you first have to fit a model, and then you look at the errors and make sure, you know, make a scatter plot of the residuals against either the x or the predicted values. You could do either one. And this plot should have no pattern. If it shows a trend, you try, we'll look at this in a minute. So this is, you do, you know, you plot histograms of the errors to see if they're normal, etc. So this is as on previous page. Once you fit a model. And we'll look at examples. So if all the 5 conditions are met, you're ready to go ahead and make inferences. All right? So let's do it. So here's an example. It's a scatter plot of the brain weight in grams and the body weight in kilograms of 34 species of land animals. There's 24 mammals and 10 dinosaurs. Let's look at this. Let's look at this data, and you'll see what I mean. All right, so let's go to the, here. Actually, before we do that, why don't we do an illustration of, because you know what, just occurred to me, it might be nice to do an illustration of like one of these, like really skewed data. Okay, so let's do that first. And you'll see what, okay, so let's look at, let's go to the PC, what should we look at? Okay, income is always right skewed. So let's see if this works. Okay, so we'll go to survey data, stat 200. Let's look at our survey data. I asked you about income here, I think. Expected income. Okay, so 20 years down the road, this is your data. How much money do you expect to make per year in thousands? So I bet this histogram's just going to look weird. Income. Yeah, look at that. Okay? I mean, you can't even expected income in thousands. Everybody's like so clumped up here, you can't see anything, right? So what do we want to do? It's just, you can't even, all right. So let's say we took the square root. That makes it a little better. Let's say we take the log. That makes it a lot better. Then we can see what's going on better. Otherwise, everybody's like smashed together, because in order, if you want to display the people who had this, think they're going to get some kind of really astronomical income, they're very hopeful, optimistic, then you can't display where most people are at the same time. So this is a much better display. Does that make sense? You can't even see it otherwise. It looks like there's something wrong. Let's look at the statistics. This is in log. They're pretty close. But let's go back to the x's. Let's do it here, and let's look at the statistics. You see how the average, this is much bigger than the median? Much bigger. So you have tremendously right skewed data. All right. So now let's go to that other data set. Now that you understand why it's useful to spread things out like that, let's go to our other data set, and that is the let's look at this. All right, so if we go to a scatter plot, and we're predicting brain from body, that's what's in your data, and you get this right here. And if you try to fit a regression, it says there's a negative correlation between the heavier you are, the smaller your brain. But that's because it's completely, it's not, you shouldn't fit, it's like a L shape or something. It's kind of crazy. It's not linear data. So we have to transform the data. So let's do that. So what are we going to do? Let's do the Y, the brain. So let's go to histograms. Let's follow our steps. So here's our brain weight. And it doesn't look normal, right? It looks right skewed. So our first step will be to take the square root. You can follow along in your notes. That does pretty well, but a log does better. And here you can create different intervals here, etc. So that's the first thing we do. All right, so now let's just go to our document camera and write that down, what we did there. Okay, so first of all, we're looking here. And it says below is a scatter plot. Okay, notice how once you make the scale big enough to see the big animals, I didn't show you who these animals are. This right here, who are these animals? You've got to check who those are. But this right here, these are really, you can see that these are huge animals, right? And these are little animals with big brains. These are huge animals. So once you make the scale big enough to see the big animals, these must be dinosaurs with small brains, most of the points are scrunched in near zero. So you can hardly see them. You can't see who they are. Now I'm curious who they are, if you don't mind. So let's just go back. You can't see them. So let's go back to here, and let's go to the scatter plot again, and see who those animals are. So here's our regression. So these, who's this? These are dinosaurs. So if you want, these are all dinosaurs here. Okay. So these are all dinosaurs here. Now, who are these? These are relatively smaller animals with very big brains. So, and this is human. So these, you can see these, but what you can't see, are all these little animals in here. They're all clumped together, or most of them are, like the pig, the mouse, the kangaroo, the horse. Well, you can see that dinosaur, but who are they? You can't even see them. The mouse, they're invisible because they're all clumped together there. So what we want to do now is to do those transformations and spread them out, okay? That's the idea. So let's go back to the document camera and just write that down. So, so you can't see these at all. So you want to transform, so the little animals, I mean, it depends what your goal is. If you want to count these little animals as much as the big ones, then you have to transform the data. If you want to count them as insignificant, then you leave them there. And it reminds me of my favorite children's book, Horton Hears a Who. You know, if you want to, a person's a person no matter how small. If you want to count those little people, or if you want to count the people who don't have much money, right? All you're going to see when you have these giant numbers are to include everybody in a graph, those giant numbers they're like outliers, or they're just going to skew everything. They're going to count a lot more, and that's all you see. So if you want to make every person count as much, every animal count as much, whatever, you're going to have to do log transformation, some kind of transformation, so they show up. And if you don't care about that and just want to focus on, but that's not what we care about here. We want to look at the relation between brain and body weight, and we get a negative one. We get bogus data unless we look at everyone. So that's the point. So is the scatter plot linear? No. So we're going to follow those 6 steps. First, what did we do? We transformed the y variable. We looked at the histogram. Which of the following best describes its shape? It was right skewed. So now which transformations do we want to use? Square root we'll try first. So we did that, and that helped some, but it didn't go drastic enough. It wasn't drastic enough. So now we did log. And by the way, it's not log base 10, it's log base E in this program. So it's the natural log. I call it log because I could call it ln, but it's log base E. That's what most people are doing. Okay? And that's what we do in our data program. Now, if the histogram were left skewed, what would we do? We'd start with y squared. We'd square it to spread out those big values. And then we go to y cubed, and then we go to e to the y. All right. So now here we are at this. This is where we are now. And we said, okay, now we have to look at a scatter plot with the transformed y and see if it's linear. So this is what it looks like. Let's just do it and see if it worked. So let's go back to our PC and let's look at that. So now we're going to go back to the scatter plots, and so we'll go, here we are, and we'll transform the y. So we said this looked good. Now it's better. Now it's better. We can see these animals. We'll fit the regression. We can see them. There's the guinea pig. See, we couldn't see the rabbit, the cat, golden hamster. So we can see them, but it's still not linear. And okay. So we have to go further. So now why don't we try working on the x? And so let's try the log of the x. If we do the same, let's put the square root first, didn't help so much. We're going to go further. We'll do the log of x, and this looks a lot better. We still have some kind of pattern. We can go further, but like it's fitting this one perfectly, the cat. Look at that. And the kangaroo, they fit really well, and Tyrannosaurus rex. But what about the elephant? Still has too big a brain. Same with the human, and who's this? The mouse, the golden hamster, and the guinea pig. Okay, so that's what it looks like. So we're going to have to do something else, but for now it looks really good. So let's go back to our document camera. And so when we just did the log, natural log of brain weight, that's on the y-axis, versus body weight, it was not linear yet. No. So now we're going to transform x as well, and we redo the regression. And now, look, it looks pretty good. We got this nice regression. Now we've got this regression equation. It's in terms of logs. This is the natural log brain weight. It says log, but it's natural log here. Okay? So now we've got a nice regression equation. For this line, it still has a pattern. We're going to go further, but it's much better. We get a plot where all the animals show up, right? Because the fitting routine also sees all the points about equally. So it comes up with a linear model with a decent R. Look at this R. It's a good R, and it's positive, as you'd expect. The bigger the body, the bigger the brain. So this is what we've got now. But the fit isn't great, but it's a good start. It still doesn't work. Here's the human, but it's great for the cat and the kangaroo. Okay, so that's what we have. And then we'll finish this next time. We'll make predictions for log transformations and then see how we'll then, but you're usually interested in the actual units. Like you're probably interested more in the weight, not the log weight. So then we'll transform back and you'll see how you get asymmetrical confidence intervals. That's what we'll do next. All right, that's it. If you have any questions, I'm letting you out early because if you have any questions on your own exam or anything you want to talk about concerning your exam, please come up now so you can take care of it now. Oh, and everybody, before I quit, people who are watching this or people online, please come to office hours if you want to look at your error sheets to get back your exams, and you can see how Scantron graded you and what you got wrong. Same with you guys in here. Bye.